Hey guys, Zong here, back with another math video. My voice is going to be kind of soft because my sister's sleeping. But today's question is finding the area under a cycloid. What is a cycloid? Well, a cycloid cycloid is the path a point takes on a circle when that circle rolls along a flat plane. This is x, this is y. So you can see if the point starts at 0, 0 on the bottom of a circle, and as the circle rolls this direction, the point sort of takes this weird curved path until the circle makes one complete rotation and the point ends up back on the x-axis. This is a cycloid, this shape right here. It's the path that a point takes as the circle rolls. It's not a semicircle, although it might look like one. It's a special shape. And today we're going to be finding the area under this cycloid. So take a moment, try to find the area on your own. Without further ado, we're going to get right into the solution. So finding the area under a curve like this, you want to have an integral, right? And to actually get an integral, you have to first figure out how to represent this point in terms of y and x. So we want to know what y is, we want to know what x is at any given point. Let's think about this. So maybe we can, this is a circle, right? And circles have this point has two properties. First, the circle has a radius, r. Let's say the circle has a radius r, like this, and it has a property theta, where the point is on the circle. I think with these two properties, parameters r and theta, we can actually figure out y and x in terms of that. Let's think about this. So let's look over here. As you can see, we have r and theta. Let me get rid of r, just theta. We know r is there. How do we express y and x in terms of this? Well, first of all, what is x? X is going to be this little sliver right here. That's how far the points travel. What about this? How far has the center traveled? Let's figure that out first. Well, since the circle is rolling, the center is going to have traveled a distance equal to this arc length right here. Because the circle is rolling, so it rolls along its arc. So intuitively, trivially, we know that the distance traveled by the center of the circle horizontally is equal to this arc length right here. And what is that arc length? The arc length is r theta. Because when theta is in radians, this is going to always be theta r, which is intuitive because 2 pi is a complete rotation in radians and 2 pi r is the complete circumference. So that's the arc length, r theta. Now, let's see if we can subtract this length right here. This length right here. I think if we can subtract the horizontal distance from the point to the center, we can get the horizontal distance that x is. So what is the horizontal distance from this point to the center? Well, as you can see from the diagram, it's r sine theta. R is the hypotenuse, this is a right triangle, and theta is the angle. So this horizontal distance is r sine theta. So then we can get x. X is going to be r theta minus r sine theta. And this property works actually even if theta is greater than 90 degrees or 180 degrees. And you can check on your own. Now let's figure out y. Y is this distance. Let's see if we can't do the same thing. We should figure out, first of all, the height of the center. The height of the center is always going to be r. So maybe we can put r here. Now let's figure out the distance from the center to the point vertically. That's going to be actually r cosine theta. This is hypotenuse, is r, right angle. So the vertical distance is going to be r cosine theta. So this thing, y, is actually going to be r minus r cosine theta. They look sort of similar, but keep in mind that x has an r theta because this horizontal distance that the center has traveled is not r, but actually r theta. So now we have some parametric equations putting y and x in terms of r and r cosine theta. This will help a lot. So let's think about this carefully. If we want to put our integral in terms of r and theta, we want to think about what it is in terms of y and x first. Well, x is going to move a total of, x is going to be the circumference, which is 2 pi r, and y is just going to be that. So it's going to be something like 0, 2 pi r y dx, right? Now let's put this in terms of our equations. Let's try to put this in terms of theta. So instead of 2 pi r, theta is going to be moved by 2 pi, because as you can see it starts at 0 and then it makes one complete rotation of 2 pi. So theta instead goes from 0 to 2 pi. Instead of y, we put in r minus r cosine theta. But we still have this dx right here. Let's try to put dx in terms of theta. Dx is going to be equal to dx over d theta is going to be able to, let's take a derivative of this, which is just going to be r minus r cosine theta. Interesting coincidence. So dx equals r minus r cosine theta d theta. Alright, that helps. Since it's just r minus cosine theta, we can just square this and put it in d theta. This is much easier to solve. This becomes 0 to pi. We can factor out this r, make it r squared. 1 minus cosine theta squared d theta. R squared 0 2 pi 1 minus 2 cosine theta plus cosine squared theta d theta. Now the first two things are easy to integrate. This just becomes give me a second. This just becomes theta blah 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 minus 2 sine theta. But we run into sort of a problem here actually. Like, how do we integrate this? Keep in mind that cosine 2 theta equals cosine 2 cosine squared theta minus 1. So cosine squared theta equals cosine 2 theta plus 1 over 2. We know how to integrate cosine 2 theta. That's just the chain rule. So actually this sort of simplifies into oh shit. Excuse my language. This sort of simplifies into r squared, oops, my brush changed, r squared integral 0 to theta 3 halves minus 2 cosine theta plus 1 half cosine 2 theta d theta. And if we get rid of this identity, that just turns into r squared 3 halves theta minus 2 sine theta plus 1/4 sine 2 theta 0 to 2 pi. Now you just plug in 2 pi in like you would for any other integral. Subtract that from plugging in 0 from like any other integral. You can solve this. It simplifies into 3 pi r squared. So actually, the area that this point covers when it moves in when the circle rotates is 3 times the area of the circle. Pretty interesting. So with 2, you have something like this.